So we would not be running this course if this is where we were heading, right? This is where we are now, and it's a temporary situation that we're fixing. And so let me explain what's going on and how it's being fixed, right? So the first thing to point out is that when you work with PITorch, we have a similar issue, right? Is like we don't write PITorch triply nested for loops either, right? And the reason we don't is that we need PITorch to have a reasonable amount of work to do each time we get it to do something, right? So we kind of say, here's a whole matrix A, here's a whole matrix B, there it all is, multiply them together, and then it says, here's the whole thing multiplied together. And that's what we do. So it's like if PITorch was an airplane, right, and we want to send our stuff off to China, we pack it all in a bag, and we put the bag in the airplane, and it gets sent off to China. As opposed to the triply nested for loop version, which is where I take a sock, and I put it in an airplane, and it flies to China and back, and then I put it in my next sock, and it flies there and back. And it's going to take, that's a fast airplane, right, but it's just not an efficient way to use it, right? So we already have this issue, which is you've got to give PITorch enough work to do to make this latency, this overhead worthwhile. Now, TensorFlow is designed in a very different way to PITorch. And for those of you that did the earliest courses with FastAI, this will look very familiar, right? And it's actually a really fascinating programming model. You say, there will be later on a float called x, and later on I will want to multiply that float by 2. Now, set up a session where we're going to do some stuff and run this computation graph, which could have lots of things going on in it, and run it in these things. Right? So I basically kind of set up this whole series of computations, and then I pass in some data. So this is a very different feel to PITorch, right? And because TensorFlow was built this way, TensorFlow, to me, does not behave like a plane. It behaves like a ship, or actually a ship designed for shipping ships, or actually a shipping ship designed for shipping ships, which is this particular one, the MV Blue Marlin. So if you have a shipping ships ship, then you need to use it in a different way, which is if you want to get all of your socks, all of the socks in America to China, you send them all, send all of your ships off to all of the ports in America, everybody dumps their socks on, and they all get sent to China, and we're all happy, right? Now, to take advantage of this extraordinary power, you have to use it in a certain way, and you have to have certain things that you need to be able to do. So like, if you're Google, and you want to run all the world's search engine queries, this makes a hell of a lot of sense. Now, TFEager is the kind of the new hot thing for TensorFlow, and it's designed to, or it does look like PITorch, right? So this is what happens when you say tf.enable eager execution, and that's becoming the default in TensorFlow. You can say, here's my number. I'm not saying there will be a number later. I say, this is my number, and this is my matrix multiplication. Right? And I can print it. The thing about this is, though, is that this is kind of syntax sugar on top of the shipping ship, right? Or whatever the hell the thing is. Because we're still using the same, a lot of the same kind of foundations, and some of it's been optimized, but only a bit. Right? So as I say this today, as of April 2019, a like 5x5 matrix, like a tiny matrix multiply on a GPU with TFEager takes 0.28 milliseconds, which is 10 times longer than PITorch takes, right? And so we still just have a lot of overhead, and so TFEager is not a solution to writing the kind of low-level, get down to the bottom stuff that Chris is saying you can do with Swift.
Yeah, but also neither are GPUs. A GPU is not going to be fast at a 5x5 matrix multiply either.
Right,
so.
Right. So I mean, it's not. You know, we want something better.
Yes.
Right. So TensorFlow has this big ecosystem of things to try and kind of fill in this issue of having this huge kind of mechanism that works in a particular way to make sure that you can put it on mobile phones or that you can do it on web servers or whatever, right? But the good news is that what's happening at the moment, and the reason we're seeing this speed, right, is that behind the scenes, Swift for TensorFlow is using TFEager. And this is like a great choice because it lets us like do this course, it lets us say like, here's how you use it, we can build things on top of it, whilst the real stuff is being built behind the scenes. And the real stuff, which is to sit on top of this thing called MLIR, which Chris can tell us a little bit about, which is basically gets all of that compiler goodness that you've seen and allow that to work with the GPU and the CPU and different types of accelerators and let you write Swift, right? So the reason I mention this is that for probably as long as this course is relevant, like the next year, the true potential of what we're talking about, you kind of won't be able to see it, right? We're actually building for a future that's not here yet. This is like a year away. But when we get there, all the stuff that Chris is showing you, we'll be able to write stuff that looks, that could even look like this.
Yeah, so if I were a different way to explain it,
yeah.
A year from now, it's going to be mind-blowing. Like the future, you're going to be able to do stuff you've never even thought that was possible and use these accelerators in ways that are just completely unthinkable unless you're writing low-level CUDA today. Like there are certain humans in the world, like Scott Gray is one of these people who can make an accelerator do crazy things that nobody even thought was possible. And that's what we're trying to do, but in a workbook.
Right, and the reason this matters is that there are vast areas of unexplored research
Yes.
territory because, I mean, most people can't write the CUDA code, and even those that can, it takes so long and it has so
Yes.
many errors that you just don't, right?
Yep.
So in a year's time, we'll be able to do stuff that people just aren't even trying to do yet.
But one of the cool things about this is you don't have to wait a year. So next lesson, we'll show you that Excellet is here today. Excellet is super awesome. It's a really important part of the TensorFlow ecosystem, and it's way better than the Torch JIT.
Right, so just to explain, yeah.
So we want to like completely jump over the industry and do something that's mind expanding.
Right.
But even today, TensorFlow has a lot of power, and Excellet allows you to express and build really cool things with super high performance.
Exactly. So Excellet is this really nice kind of intermediate thing where it's much more mature than the PITorch JIT. It's been around for a couple of years now.
Yep.
It's a compiler that will turn your code into stuff that's kind of similar-ish performance to what you might see from PITorch JIT, probably a lot less rough edges.
Doesn't generate blobs of C++ and try to compile them again. And yeah, it's a principled compiler.
So it's a really neat path because it allows us to do this course now. It allows you to start playing with this now. Yep. In a couple of months, it allows you to get a lot of performance for a lot of things that you might want to play with. And, it means that by the time that MLIR comes, we'll be all ready to hit the ground running.
Question. Is there a way to make sure the matmul or other functions are correctly using shared memory on the GPU? For example, using tiling to make sure you aren't constantly busting the cache of shared memory on the GPU.
Yeah, we're going to talk about this next week, so maybe we could wait back till then. Or?
So I think that the thing to know is that this is not something you would write in Swift for TensorFlow, right? You would not poke a tensor one float at a time. It was just not designed for that. And so you can go through all the steps. This is very similar to the Python workbook. But what you end up wanting to write is, let's see here. Well, you just write this, where you write something where you take two matrices and you multiply them together. Or you use the Unicode one or the matmul one, and it goes fast. And it takes 0.02 seconds, which is faster than the Swift version because it's using the GPU. It's properly tile blocked. If you run on the CPU, it uses all the threads on your computer, and it goes really fast. And so the way to think about Tensor is that it's meant for these big operations. Right? It's not meant for one float at a time. And
we will see next week some really interesting stuff coming down the line, with stuff where you can write kind of tiled algorithms in ways that are much more concise than the triply nested for loops, but much more flexible than the matmul.
Yeah. John.
Sorry, another question just came in. How do LLVM, MLIR, and XLA relate to each other?
That would be better explained with slides, which we'll go into on the next time, I think. But LLVM, the simple way to explain it is that it is really good at CPUs. It's a little bit of an oversimplification because we do use it for some GPU stuff, but LLVM really helps you with the one float at a time kind of a thing if you're going to a simpler processor. Excellet is really good at tensors, and so it's a tensor compiler, and so it's really good at saying, I have these big tensor operations, I have convolutions. To get maximum performance out of a CPU or a GPU or a TPU, for example, you have to know about tiling, you have to know about fusion, you have to know about a lot of these low-level systems things before you then hand it off to LLVM that does the low-level stuff. And so Excellet talks to LLVM for GPUs, for example, and for CPUs. And the way to think about it is Excellet does all the tensor stuff and LLVM does all the float and small vector stuff. MLR is like Excellet in a certain way, but it's tackling graph-level optimizations in TensorFlow and kind of expanding Excellet beyond just dense linear algebra, because there's a lot of interesting sparse things and other things that are coming down the pipeline that are really exciting. So
I mean, basically, we won't look at the rest of this notebook other than to say that the broadcasting stuff that we saw is all here. So you can kind of see how that all looks. At the moment,
you can run ops on the CPU or the GPU. All that kind of stuff.
All that stuff is all here, and it's don't worry about the performance. It's really slow at the moment for the reason we mentioned, but it totally won't be. And you can also see matrix multiplications at different sizes and how to check its timing and so forth. So did you want to go to raw now? Or?
Well, do you want to do this, or do you want to go to 11? Do we have time?
We have time to do this now.
Okay.
Maybe
so
5 to 10 minutes.
Okay, cool. So one of the really cool things about the stack is that TensorFlow is a really mature ecosystem. It has hundreds of different operators available. There's pros and cons of this. So TensorFlow kind of grew organically over time a little bit, and so it has a lot of things in its toolbox. What Swift for TensorFlow does is it tries to curate that, and it has tensor. And the way tensor works is it's the struct, and the struct is implemented in terms of those low-level tensor operations. And so if you look inside tensor, and here there's a link so you can go click on it and see the implementation. Tensor has this thing called tensor handle that is under the covers basically the TensorFlow low-level thing that eager mode uses. And then if you look at plus, what plus does on two tensors is it calls this raw add operation. And the way that this works is this is just directly talking to the add op in TensorFlow. And the add op is implemented with cuDNN, or it's implemented with Excellet, or it's implemented different ways for different pieces of hardware. But this is just a simple syntactic sugar thing where we're saying, hey, plus turns into TensorFlow add. Now, again, TensorFlow has tons of cool stuff, and it has stuff that I barely understand with lots of mathy things and triangular LU decompositional things and like Bayesian propagation of things that
We have an excellent course about triangular decomposition if you
Awesome. I'm going to try to survive next week, and then I'll take it. And so we haven't curated all of the things that are potentially interesting. And so what you can do is you can actually add new things to Tensor. And so one example of that right here is, so you can get like zeros like. If you go into here, let's see if this is, so with tab completion, you can see all of the interesting things. Add many sparse to tensor map, add n, adjust contrast, assign. Like it's got lots and 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 lots of.
And this is super cool, particularly if you're watching this between like about April and about September, like in the the period where maybe the XLA stuff isn't as fleshed out. You probably care about this because there's stuff you can do, which we haven't necessarily surfaced yet. So, for example, somebody today was saying, "How do I can switch from RGB to BGR format?" And somebody said, "Oh, there's something in TensorFlow called reversed," and so here's the answer: raw.reversed.
And so
worth knowing about this.
Yeah, and so one of the things we'll use for XResNet and other image models in this course is, hey, we need to be able to load a file. And you can do that with Python, that's fine. TensorFlow has great stuff for doing this. And so here we just use raw read file. And so all we're doing is we're adding a method to string tensor. And we're saying, hey, if you want to create a string tensor from a file. We can have read tensor. We can just use read file, and now I can say string, give me a string tensor, read file, foo, and I added a decode JPEG method on here too, so now I can say decode JPEG, and I got my file, right? And so this is one of the cool things about this platform is that TensorFlow has all this functionality. We're not trying to hide it, we're just trying to curate a little bit, but again, you can just go add whatever you need.
Yeah, so one of the people in the study group today was building an audio library with Swift for TensorFlow, and we haven't surfaced any of that, so they were grabbing raw.decode WAV or something, and they had it all up and running.
And it's super cool. And again, Swift gives you nice ways to build these things as APIs with default arguments and all this nice stuff, and so you get a lot of design space to do things that work the way you'd like them to work.
Cool. So the way we're going to do this is we've kind of gone like super bottom up. I must admit I thought we had done bottom up before, but this is another level of bottom up.
Then he brought a compiler guy.
Yeah, then we brought a compiler guy who is always good at making me feel small and insignificant. And so, but now let's jump back up to the top again to see where we're going to end up. And then next week, we're going to kind of flesh out all the stuff between the middle, right? So I'm going to jump to Notebook 11. And Notebook 11 is interesting because this is the one where we train an XResNet on ImageNet, right? So this is where we're heading. So every time we import the previous notebook, just like we do in Python, the previous notebooks, however, aren't just numbered, but they also have the name. That's the only difference. And then this is the equivalent of %matplotlib inline in this environment. So here, load data. We'll show you how we built something that downloads ImageNet, but it basically looks almost exactly like the, very similar to the download MNIST thing you've already seen. And we've created an item list, which has extensions. And we've created a split data, which takes an item list. Now, one of the nice things here is that we don't really need something like functools.partial in Swift, because now we can just pass in a trailing closure, which, as Chris described, if the last thing is in the last parameter is a closure, then you can just whack it in curly brackets. You don't even need a return or anything. And you don't even have to give it an argument name because you can use the default ones. So we're saying split this item list by grandparent. This is the file name that you're going to get. So this is basically like the equivalent of doing partial, right? And it's going to be some different validation set. And so now we can create our labeled data, and we need a processor. So we have, again, a category processor. So you can see we've got a whole data blocks API here. One of the things that I guess you're going to talk about next week, Chris, is and mutation and stuff?
Sure.
Yeah, okay. So basically in Swift, as Chris mentioned, most of the time we use structs. And as Chris will describe to you, structs are things that normally don't change. But you can create something that kind of feels a lot like a C++ reference or a C pointer, but it's much cooler by adding an ampersand. Because remember, processors actually change their state because we get like a vocabulary, for example, the first time we use a processor on the training set. So now we've got a split labeled data set. And then we've added a to data bunch, and we can pass in all the normal stuff, including a batch size. So next thing we can do is we can do transformations. And again here, we can use a trailing closure to basically do a partial, to say that we're going to do resize in our transformations. So then we'll grab a batch. Something that I think Chris will probably talk about next week more is this thing. But basically, in Swift, very often you want to be able to say, hey, this is going to return either a batch of data, or maybe it was going to return nothing at all, right? Which in Python, we use the optional type for that.
None.
And it's called the same thing in Swift, right?
Yeah, none.
None.
Optional.
Yeah, so if basically what happens is if you have something that might not return anything, so one batch might not return anything because there might be nothing to return, it can return nothing, and then exclamation mark just says, assume that it's something. So we can look at the shapes of that batch, and look, we've even got show batch. So it's been really fun, this process of, in the last couple of weeks of basically saying, what does FastAI look like on Swift? And one thing I'll say is, like, a lot of these notebooks have been written by Sylvain in particular, and by me a little bit, and we don't know Swift at all well, so any good Swift programmers looking through those notebooks thinking, oh, this is nice, but it'd be even more Swifty if you did blah, please let us know in the forum, because we're super interested to learn how to write better Swift.
And I've been super interested to learn all the ML. It's been great.
It has been great.
I mean, it's been great working with each other.
I mean, it's in one sense, it's a good sign that you're learning FastAI for Swift from the people who started the FastAI and Swift projects. But on another sense, I know nothing about Swift, and Chris doesn't know much about deep learning, so maybe it's the worst of all possible worlds. I don't know.
No, I think we're all learning together.
Yeah. So anyway, yeah, it's been super fun. So as you can see, we've got a data blocks API that's now working. The other thing I'll mention, as you'll see next week, is the way we've got this working is it's using a TensorFlow API called tf.data, which is actually a lot better than a lot of data APIs, but it's still not nearly as good as I would like. And I would love to, as a community, start building out the next version that uses like Swift's libdispatch to do the threading, and maybe OpenCV to do the transformations and stuff like that. Like, we can build, I think, a data blocks, something like the Python data blocks API, but that is like native. It's not talking to anything else.
Yep.
Anyway, so now we've got batches of data. We can train a model as soon as we have one. So let's create a ResNet model. And as you've already seen in the slides, it ends up looking very, very familiar. So here's our conv layer. Just one thing to mention, at the moment, and this will probably only be true for a couple more weeks, there are kind of two versions of all the layers. There's the versions in the FastAI repo, which all start with FA, and there are versions in the Swift repo that don't. So just ignore these FAs. So a conv layer has a batch norm, and it has a convolution. Another thing that's slightly awkward at the moment is that so you'll see right now, some of our code looks weird because autodiff in Swift doesn't support flow control, so if or for loops. That'll change soon enough, right? So when you see something like no bias convolution, that's because we can't write a convolution layer that has an if statement saying if the person asked for bias, use it, otherwise don't. Right? So don't worry too much about those workarounds either, they'll go away soon enough. So we've got a batch norm layer, we've got a conv layer, and we can go through them, and the 0BN is the stuff that you're used to. And as Chris said, dunder call is spelt without the dunder, but otherwise everything looks the same as usual. Because we don't have the ability right now, this will change soon, to use if in differentiable code that needs to be differentiated, we've basically added something called a switchable layer, which is something you can turn on or off, so the details don't matter. Chris will describe next week, however, how we actually wrote our own kind of custom gradients for this kind of layer, and that'll be fun to learn about. So then we used that to basically have something where, because remember in ResNet, in the identity path, it's not always an identity path. Sometimes you downsample in that path, sometimes you change the number of channels in that path. If you downsample, then you maybe add an average pool 2D. So because, again, we don't have the ability to have if, we just use this switchable layer, and maybe you change the number of channels by adding a 1-by-1 conv. So that's all that is. So most of this stuff, if you're watching this, much later than kind of July or something, this will probably all have gone away and been replaced by some if statements. But once we've got all that, the res block, there's really nothing to mention, is there? I mean, it's basically identical. If you look back at the version in 11 in the Python versions, and kind of switch between them, you almost need like a strobe light thing to see that they're different. Like it's the same layers equals conv layer, layers convs equals conv layer. Don't know why we changed the name. Got this ternary here. This question mark and colon is identical to if and else as an operator in Python. Comes from C. And then finally in the call, that and that look exactly the same.
Pure selves.
Yeah, thank heavens. Thank you. Yeah. Make layer looks basically the same. This is the make layer we had before. This is the make layer we have now. Don't need that. And so it's interesting to see how some Swift things kind of come out quite neatly, right? So this use of map. So this is generating, this is the same as range and blocks in Python. So this is basically saying map, range, and blocks, and then passing in this closure, which generates the res block, right? So I think it's kind of, I don't know, I find it more clear the Swift way, but very, very similar.
And the idea of Swift is to have simpler primitives that compose.
Yeah.
Instead of having special cases for the important things.
Yeah. So now we've got all that. The ResNet looks very similar to what we would expect. We've still got our number of filters thing going on. The stem, so now we've got that array map thing. You kind of start to get a feel for these kind of idioms in Swift. So kind of range.map is a useful kind of idiom to be aware of.
You can also use a for loop. You can say for I and 0.3. That's also fine too. Just depends on how you want to write the code.
There's an enumerate, but rather than enumerate bracket something, it's not enumerated, but it works the same way. When you map to it, you get back an index and an object, just like in Python. So very familiar. So in this case, because we've gone .map and then .reduce with plus on a list, this is a list comprehension now, right? Because this is spitting out a bunch of lists that we're joining all together. So no special cases there. This is one of those cases where you're asking for the last element of a list. List could be empty, so there might be nothing in it. So exclamation mark says, just assume that there is something there. And we've written a little compose. So we can compose this list of layers on our input. So again, we've got kind of similar concepts expressed in similar ways. So we can now put all that together, and we've got all our different ResNets. So now we create the various functions that we need to pass into our ladder. So one is a function that's going to create a model. So it's going to be something that creates an XResNet, and that's the function that's going to create a model. We're going to have a function that creates our optimizer, which, as you'll see, we have a stateful optimizer, just like we had in Python. We have a learner, just like we had in Python, and it has very, very similar look to it.
And again, next time we'll talk about how all these are built. And so Atom Optimizer, of course, is just a thing that's hackable.
Yep.
You can change it.
Exactly. We have recorder callbacks, just like we're familiar with. We have one-cycle training, just like we're familiar with. This add one-cycle delegates and make default delegates is probably going to go away pretty soon, and we'll have some slightly neater ways to do this. So by the time you see this notebook, this might have changed a bit. And then we train it with a ResNet 18 for a few minutes, and we're at 0.81. A couple of things to mention as I go through this end of April. Right now, this uses about twice as much memory as PITorch, and it's about 3 to 4 times slower than PITorch. No fundamental reason why this need be the case. It's just we've just started, and so the fact that within
it's not bad for 3 weeks.
Not bad for 3 weeks. I mean, and all the
from nothing,
and all the work that you guys did to build the auto diff in the first place.
3 weeks ago, it really didn't work.
Yeah, so it's pretty cool that we're at a point where we can actually train proper models like this from scratch in like not too slow and not too memory intensive. And if you're interested in kind of getting into the weeds, we would certainly love help with fixing the performance and fixing the amount of memory.
So there's a related question. What would be the best way to contribute to the Swift for TensorFlow ecosystem as someone who's now using Swift for the first time?
Yeah, that's a great question. So the best place to go is github.com/tensorflow/Swift. That's our landing page. There's also a bunch of tutorials there. It explains how to get and build things. One of the things that we're doing is that we're building everything in the open. And so we do our development in the open. We use GitHub. We have our discussions on a mailing list that you'll find linked off our GitHub page. And so we try to have a really inclusive and welcoming community, and there's a ton of resources available and a lot to do.
Yeah, and I would, that's one way to do it. I would like to suggest another way, which is to come to the Hairbrained Forum or the FastAI forums, because I think for a lot of people, the right way, the best way to contribute, the way that you'll get the most out of, that will be most relevant to you right now, is to pick something that you've already been using in Python and doesn't exist yet, and create the Swift version. And you may think you have no idea how to do that, and perhaps you don't, but like create a really crappy, slimmed down Swift version and build from there. That's the only way any of this stuff gets done. Ask for help on the forum, offer help to others, and so like pick small bits or find some piece that hasn't been documented yet. We haven't really figured out yet where
To put things?
Yeah, where FastAI lives and where Swift for TensorFlow lives and where different repos will be. But, in the end, between the, FastAI and Swift for TensorFlow repos, there'll be a kind of an ecosystem that covers the same kind of ground that PITorch plus FastAI covers and has just as much room for you to, well, much more room actually for you to build things on top of that, because you've got like the entirety of Scikitlearn and Matplotlib and pandas and all this stuff to...
And another thing is if you go on the FastAI GitHub, you'll see these workbooks. And we skipped from 1 to 11. And so next time we'll go back through and talk about 2 and 3 and 4 and 5. But these are all there for you now. And so if you'd like to look, you can go do that. And they'll get a little bit better by next week, I bet.
Yeah, and one thing to mention is where else with the normal FastAI notebooks, we nearly freeze them. Once we do the course, we just fix errors, and that's about it. These notebooks is going to be very different. We're going to keep them very, very up to date. So by the time you watch this, they may look very different, because we want to always have for you, showing you, like, this is how we suggest you write Swift for TensorFlow code now.
And even over the last week, we've been, if you look at the GitHub history, you'll see we've been discovering new things like differentiable arrays and switchable layers, and it allows us to delete lots of previous workarounds, and the next weeks and the next couple of months will be similar. So,
Do you want more questions
Sure.
now? All right. Is Swift thread safe?
yes, Swift is both thread safe and has a really great threading abstraction called dispatch. And so you can fire up lots of concurrent work items, set up work queues, has a really vibrant and good API for doing that with quality of service and like all these advanced things that are available there.
Yeah, I've never used such a nice kind of threading. It's like it's a framework. It feels more than just a language. So like on the Apple side, they call it Grand Central Dispatch, but they've ported the whole thing over to Linux. And you have this whole kind of threading library framework, which is super easy to use and extensible. And
this is one of the reasons the Swift on Server community really likes Swift, is that it's efficient, yes, but it also supports threading and other things really well and very naturally.
Cool. Are there any Scikit-Learn for Swift projects in the works?
I have no idea. There should be.
Yeah, I haven't seen anything much. I have a random forest implementation I would love to convert over to Swift, which is a pretty nice one, but we'd definitely be nice if you could build a gradient boosting machine, or even simple things like k-nearest neighbors and stuff like that. Yeah. I think I think though that the opportunity here is to go beyond just reinventing what's already there. Like Scikit-Learn is cool that it exists, but it could be a lot better, particularly in Swift. So if you do decide, I want to build bits of sklearn or bits of pandas, jump on the forum and talk to us about about it, and let's try and build something that's vastly better than what's been before, not just a copy of it.
I wouldn't suggest that being a starter project. Like if you want to start a project, pick one of the lessons in the 1 through 7 class and implement some of those algorithms. I think in terms of this framework, I think that'd be a really great place to start. But as you get more experience and you get more familiar with Swift, then tackling something like building a big library can be a lot of fun.
Is there any plan to build Tensor Shapes into the Swift type system?
So we have a Tensor Shape type. It's a struct, literally, right now, and that's what when you pass in shapes to create a tensor of zeros, you get that. I think what they're probably asking is, will we get dimensions in the types, or will we get names in the dimensions? So this is something we're super interested in. We think there's a lot of opportunities there, both in terms of like shape checking, for example. The whole stack we're building with the compiler integration and the good the locations and stuff like that, we think there's a ton of potential. We haven't tapped into that yet. The names on dimensions is tricky, and there's lots of space, and we haven't exactly figured out how the best way to do that is, because there's trade-offs, but that's exactly all the kind of like second step things we want to do, probably starting this fall-ish, when the basic autodiff, basic performance, like scale out, and a bunch of other things are all settled, and we feel good about all those basics. And we're trying to stay focused on making sure that things are really good and build the basics and get them right, and then move out. Yep.
Okay, any more questions?
There are allocations.
No, I mean that's fine.
We're at a good stop.
Okay. How is ampersand referencing different from struct?
Oh, we'll talk more about that next time. So Swift has this comes back to safety in the language. Swift has a completely different approach to references, like classes and structs and values. And so I'm going to save that mind-blowing piece for next time. It's really cool.
It is.
It underlies a ton of, I mean, it's a very foundational thing that makes a lot of stuff possible.
And how is Swift for probabilistic programming?
Ooh, so this is one of the areas that I'm both completely incapable of talking intelligently about, but also very excited about, because this is one of those things that I think is really underutilized. One of the things that I think is really interesting about Swift as a platform for machine learning is that you often, with Python, you end up in this weird situation where you build a machine learning model, and then you have an application that you eventually want to use it in, and these are two different things. Training your model and deploying your model are different worlds. And we can start erasing some of those boundaries, because Swift can be put in a mobile app, believe it or not, or put in a server, or put in other things that you're actually deploying. And probabilistic programming and many of these other applications, I think would be great to build and integrate with the applications themselves.
So I think the answer is it'll be a great fit. I haven't seen anything here yet, but basically with things like probabilistic programming or things like kind of graph-based systems, they're not a great fit for PITorch, and that's not a controversial thing to say, because Sumit Chinchilla, who created PITorch, said that on Twitter himself last week. He said if you want to do this kind of work, at the moment you might want to look at Julia, which is another great option for this kind of programming. Because what happens is you have these kind of deep connections, computational graphs of lots of things calling lots of other things, and so you need, and they're often kind of small, so you need those things to happen super quickly. So things like Julia and Swift work really well for that kind of thing, particularly when you kind of add all the threading stuff on top as well. So if you're interested in that area, that would certainly be one that I think you could start getting into straight away. Like, one of the nice things about that is you can do a lot on the CPU. Like, a lot of these things don't even make sense on the GPU. So you can probably, take advantage of it right now. And for that, actually, we'll add it to the forum post, but I actually have a post already about how to access a variety of random number distributions from Swift, C++ random number distributions, so you could actually get started with this right away. Is that it?
Yeah, also the TensorFlow ecosystem has a big mature framework called TensorFlow Probability. And so I personally don't know very much about it, but I expect that all the atoms you need are all there, and we just need somebody who knows the space really well to build a Swift library that can expose all the primitives that TensorFlow already has.
Is that it?
How could you deploy Swift models on Android?
Well, so I think there's two options that you have there. So one is Swift, again, builds on the entire TensorFlow ecosystem. And so TensorFlow ecosystem includes graphs, and graphs are part of what Swift talks to. So you can export a graph, you can send it through TF-Lite, and so the whole mobile deployment situation there works.
I feel like that's kind of the model we're trying to get away from a little bit, though. Do you feel that way?
So the other option is, like, Swift actually runs fine on Android. People ship Android apps written in Swift, so you can do that too. Swift on Android isn't really awesome as far as I know. I'm not exactly an Android programmer. I don't really know that. But the issue there is that Android, you have a dual world between the Java stuff and the native stuff. And so Swift fits into the native stuff, is my understanding. But I know that people are building and shipping Android apps written in Swift. And so that's a totally reasonable thing to do.
The other thing to mention in terms of platforms is that Swift on Windows is starting to come together as well. So I don't know where it'll be by the time you're watching this at home, but Swift is definitely making its way to worlds outside the iOS world pretty rapidly, and Windows is one of them.
Yeah, it's super exciting. I mean, people are writing, what's the Windows MVC? MFC apps in Swift, which is brain twisting to me.
So what we're going to close with now is a little taste of where we're heading next week. And this is actually something that Rachel shows in her computational linear algebra course. And it comes from a really amazing programming language called Halide. And Halide is one of these like dramatic steps in terms of like completely rethinking how we program computers. And I want to show it to you because it gives you a sense of the kinds of problems that Swift has to solve in order to, like the goal here is to be able to get, this performance. Because remember, the C speed triply nested for loop was 0.07, but TensorFlow is 0.02, right? How do we get this level of performance, but you being able to write it yourself in Swift? Now here's why it's hard, right? And so this video actually comes from the Halide project, which is a programming language that has kind of invented an amazing way to think about this. And so I'm going to use it to describe the problems that we're going to solve. So in order to write something fast, we have to think about how everything's going to get put together. And so the algorithm we're going to write here that they wrote in this Halide video is one where they're doing a simple blur, a 3x3 blur, right? So we take each group of 3x3 pixels and we take their average. That's how you do a 3x3 blur. Now, what are some of the things we could do, right? So in what order, for example, do I compute the values in my 3x3 blur? And one way is just go through each x one at a time, and then within that, go through each y one at a time. That would be one choice. A second choice I could make would be to do the exact opposite, which is to go through each column one at a time. Now, these aren't going to have very different characteristics. Maybe the latter might be a bit slower because we're jumping further through memory. But what we could do is we could do something called vectorization. And vectorization is super important because what happens with vectorization is we actually take 4 or sometimes even 8 numbers at a time and throw them all at the CPU or GPU at once and say calculate them all together. And so we have these things called vector units in our computers nowadays that can do that. You can even have multiple vectorized things happening at the same time because you have multiple cores. And in fact, in the GPU, this is what happens all the time. Or, in order to think about kind of better memory access, we could kind of do a little block at a time, like this. So there's like lots of choices about how I compute my values that are going to change the performance characteristics of my, in this case, a blur. Another question is, when should I compute my inputs? So here's my input. And see how it's going through 3 at a time, right? So because I'm trying to calculate 3 at a time, and that gives me my blurred in X. Now I have to go through all of those 3 at a time. And so you can see this is super slow, it's recalculating things again and again, and it's not able to really use the cache well. Instead, I could do a whole set of 9 at a time, and that would then allow me to create a whole blurred output at a time. Or I could go through it like this, exactly like before, but actually save what I had before. And that means when I then do the next row, I don't need to recompute because it's already there.
Okay, just add a clarification that the left panel's input, the middle is the intermediate values, and the right is the final output.
Thank you. We could vectorize that. So we can do vectorized input and then vectorized on the intermediate values and then calculate those to create our vectorized output with parallel processing. Here's another way that we could combine vectorization and parallel processing. There's all these things you can do, and you can see they're going to have very different performance characteristics, right? So at Halide, they have this neat idea, which is, hey, let's not write nested for loops and tiles and looping through the memory like that. Let's instead describe for each value x comma y in my blurred output, here is how it's calculated in this kind of declarative way, right? This is like literally the definition of a blur algorithm. And so you first do that, and then after you've done that, you can then say to Halide, what are different schedules for calculating that? So what's the kind of order in which things are done? And for these different schedules that are written here, they have all the different behaviors you just saw, right? Now, here's the thing, right? When expert CUDA programmers and expert CPU programmers write code to do things like this, they're using the world's best knowledge available across all of those things to create special versions for every architecture, for every different, well, not every, but lots of different matrix sizes, tensors of different numbers of dimensions, so much assembly code, right? And so we can't write that, right? So how are we going to be able to write the stuff that's in our head, but have it run reasonably quickly? And so what we're moving towards with stuff like MLIR is the ability to kind of have like domain-specific languages where you could write like, here's the tiling domain-specific language, and here's the, you know, and the...
For example, Halide directly.
For example, Halide directly, right? And so that's the hope of where we're going to be going here is that Chris's team is going to be putting these kinds of tools in your hands via Swift.
Yeah.
Is that a reasonable summary?
Well, and so one of the bad things about Halide, so in this space we have TensorFlow today, we have Excellet. Excellet is an important part of TensorFlow right now. It's just not really wired into the Swift part of TensorFlow yet. Excellet does all this stuff right now. And Excellet is really good because you don't have to hand tune it, like that whole writing out schedules. Excellet does a good job of using the hardware as it is today. The thing we're going further with MLIR is to say, well, instead of you having to put all this blood, sweat, and tears in to tune it and know the hardware and do all this stuff, we can do other things like search.
And in fact, there are research systems available now which will use genetic algorithms to auto-search for an optimal schedule. So you're starting to see the kind of the ideas that come out of the database query optimizer world coming into the CUDA kernel world, and like, this is going to be so great for us data scientists.
Exactly. Search can be implemented in lots of different ways. Brute force, reinforcement learning, like lots of different genetic algorithms. There's lots of cool things that can be done here, and so what we're going to do over time is crack open the compiler and make the internal algorithms all learned, and I think that's going to be super cool. So
this is why you have a compiler guy and a DL guy standing next to each other, right? Because
but we like each other too.
Oh, you're okay. Because we're not going to get this kind of great outcome unless people like us are working together with amazing teams like the folks that they have in TensorFlow and Excellet and so forth. So next week, come back and we will dig even deeper. Thank you very much, Chris Lattner.
Thank you, Jeremy.